going to look at finding the components of a vector if you know the magnitude and the direction angle. So there is a formula for that, and it's right here, and I want to talk about where the formula comes from. Alright, so I have a picture here of a right triangle. So we're going to imagine that this is the origin, okay, and we're going to imagine that this is the vector that I've graphed that comes out of that origin, and let's say that that's the initial point, here's the terminal point, and the vector points in that direction. If that's the case, then the components of that vector would be here, so that's how much I would move to the right. I would call that A. So there's our x component, and how much I would go up from there, that's the y component, we'll call that B. Okay, so let's assume that we don't know what A and B are. So those are the things that we're trying to find. And let's assume that the things that we're actually given and the things that we actually know are the direction angle. So that would be the angle that's made with the positive x-axis and where that vector stops. So starting at the positive x-axis, we'll rotate until we get to that stopping point of that vector. So that's what we call the direction angle. So let's say that that is actually something we know that we're given, and we actually know how long this vector is. So I know the magnitude of the vector. So assuming I know the angle made with the positive x-axis and I know how long the vector is, could I determine A and B? And so the answer is yes. And so how do we come up with that? So let's look at this idea here. Our right triangle trigonometry would tell us that cosine of that angle theta would be equal to the adjacent side divided by the hypotenuse. This is our SOHCAHTOA. Alright, so if that's true, then cosine of that angle would be A, that's the adjacent side, divided by the hypotenuse. Now, when we talk about this, we're talking about the lengths of the sides of that triangle. So that would be dividing by the length of the vector, so the magnitude of that vector v. Now remember that my goal is to try to solve for the value of A. That's what I'm looking for. So in order to get to that, I'm going to multiply both sides by the magnitude of the vector. Okay, so though we cancel out here, and I'd be left with A is equal to the magnitude of the vector times cosine of that direction angle. So that goes here. So that's our x component, or that's that value that goes in front of I. So remember, when we talked about that ij notation for the component form of a vector, the letter A is the x component, that's the number in front of I. And so if you know the magnitude and the direction angle, then you can easily find that A value by just plugging it into that formula. Alright. What about magnitude times sine theta? Where does that come from in our formula? Okay, so this time we're going to use sine theta. So using SOHCAHTOA, sine of this angle would be the opposite side, which would be B, over the hypotenuse, which is the magnitude of the vector. Alright, now once again we want to solve for B, so I'm going to multiply both sides by the magnitude of the vector. Cancels out there, and I'm left with B by itself, and on the left hand side I have the magnitude of that vector times sine theta. So that's how we get that second component, or the number in front of J, to tell us how much we're going to move up and down. Alright, so we are going to see this formula pop up a bunch, so you want to keep that handy. One of the things you want to make sure that you're careful about is that any time that you put an angle into this formula, you are making the assumption that the angle is made with the positive x-axis. Alright, so let's look at an example using this formula. We're asked to find the vector with the given information, and we're asked to write our final answer in that component form using that IJ notation. Alright, so we're given that the magnitude of the vector is 8, and that the direction angle that the vector makes with the positive x-axis is 45 degrees. So I'm going to sketch this. So I'm going to sketch it as a position vector so that the initial point is going to start at 0, 0. And we're going to rotate 45 degrees for our angle theta. And we're going to draw our vector. And we're going to say that it has a magnitude of 8 units. So it's 8 units long. Right, so we want to find the components of the vector. So we're going to use that formula above. So let's fill some things out. We know that 8 is the magnitude and 45 degrees is that angle. Alright, we're going to find two things. I'm going to find the exact value, and then we're also going to work with the approximation. So the exact value would be using the unit circle to calculate the cosine and the sine of that given angle. So that would be 8 times the ratio plus 8 times the ratio. You want to make sure here sine and cosine are going to go away because we're finding cosine of 45 degrees. That's quadrant 1, so that would be a positive square root of 2 over 2. And sine of 45 degrees, also quadrant 1, so positive square root of 2 over 2. And we're going to simplify that by canceling common factors. Think about that as 8 over 1, 2 goes into 8 4 times, so that's 4 times the square root of 2i plus 4 times the square root of 2j. Alright, so if you were asked to find the exact values of the components of that vector, you would use the unit circle to find those ratios for sine and cosine, plug them in, and then we have not used our calculator at all. Now, if you're asked to find an approximation, which you could be asked for either one of those, we could put this into our calculator and let our calculator do the work. Alright, so I'm going to go to Desmos. Alright, one thing I suggest when you're in Desmos and you're working with angles is that you make sure that Desmos is in the correct mode. So if you're working in radians, then use radians. If you're working in degrees, make sure you switch modes. We are working in degrees, so I'm going to go ahead and switch to the degree mode. And I'm going to type in 8 times cosine 45 degrees. Alright, so that gives me about 5 point, let's say we round to the nearest 1 decimal place, so that would be about 5.7. Now it would make sense here that the second component would be exactly the same, and so our approximation would be exactly the same, so it should be a positive 5.7 in front of j. But let's confirm that into Desmos. I'm going to pull up Desmos and we'll type in 8 multiplied by sine 45 degrees, and those numbers are exactly the same, and that makes sense. So we'll go back to our notes, 5.7. So what have we actually found? Let's just make sure we understand that. We found that if we start at the initial point of this vector, we would go to the right about 5.7 units, and then we would go up from there also about 5.7 units. So we found that A value and that B value that represent the components of that vector. Alright, let's look at another example. I recommend that for these that you draw a picture and think about what quadrant that your angle is in. So we're given that the magnitude of our vector is 10, and we're told that the angle is 240 degrees. So I'm going to graph my vector starting at 0, 0. I'm going to graph it as a position vector. So my initial point is there, and we are going to start at the positive x-axis. We're going to rotate 240 degrees. And then we're going to graph our vector. We also know that the length of this vector is 10 units long. So we know the magnitude and the angle, and we know that we're in quadrant 3. Alright, so we're going to use that formula. Alright, so for the magnitude we're going to put 10. For that direction angle we're going to put 240 degrees. Alright, so let's start out by finding the exact value. So I am going to say 10 times, and we're going to find out what are the ratios for sine and cosine. Now when you do this, you are going to replace everything in that box with a ratio. So sine and cosine are going to go away. So what is the cosine of 240 degrees? If we're in quadrant 3, in quadrant 3 we got all students take calculus. Sine and cosine are actually both negative in quadrant 3, right? So I'm going to put a negative sign here and here. And we're talking about a reference angle, is that 60 degrees? So our reference angle family, 60 degrees. So do we know the sine and cosine of 60 degrees? What would that be? 1/2 for cosine and square root of 3/2 for sine. Okay, so make sure you know the sine and you know the ratios based upon that reference angle. Now if we want to simplify this exact answer, I'm not going to put anything in my calculator because I don't want to round for the exact answer. I'm just going to simplify those fractions. So 10 and 2 have a common factor of 2, so 2 goes in 2 once, 5 there, so I get negative 5i. And then here 2 goes into 10 5 times, so I get 5 square root of 3. And I want to be careful there, I have a negative. I want to make sure I put that negative out front. Positive times a negative gives me a negative. And that's the number I get in front of j. So when you're asked for an exact value, we're looking for using that unit circle and our knowledge of all students take calculus to answer that question without putting it into the calculator. All right. If I want an approximation, which sometimes the approximation comes in really handy as well, I can use my calculator. Now for the first one I really don't need an approximation because I already know what that is, but we can put that into our calculator anyways just to simplify. So let's just practice that. 10 times cosine of 240, right? So 10 times cosine of 240, I get negative 5, so there's no rounding there. 10 times sine of 240. So for that I get a negative 8.7, rounding to the nearest one decimal place. So negative 8.7. Alright, so once again I do want to confirm that this makes sense with what we've drawn in our picture. So what we found is the components. So if I start at 0, I would move to the left exactly 5 units. So the sign is important there, right? Because the negative on there would tell me to go to the left. And then the sign in front of j is negative as well, so it tells me to go down. So I will go down about 8.7 units approximately. And so to get from the initial point to terminal point, we'll go to the left 5 units, down 8.7 units. The signs in front of those components are helpful in telling us where that terminal point is going to lie.